So good evening students. In today's lecture, we will study NCERT Chapter 7 exercise question and NCERT Exemplar questions. In exercise questions, we will be covering 7.1, 7.2, 7.3 and 7.6. From Exemplar, we will be covering 7.18 and 7.24. This is the disclaimer. Let's start with the first question. You have to assign oxidation number to the underlying elements in each of the following species. You can see 3 species and each of this is having one atom as underlined. Let's start with the first one. So the first one is NaH2PO4. Here the phosphorus is underlined. We will assign an oxidation number of X for the phosphorus. We know that from our previous knowledge that oxidation number of sodium is always taken as +1. Then hydrogen can show a maximum oxidation state of +1. So obviously for metal hydride it shows a minimum oxidation state of -1, but here it will show +1 only. What about oxygen? So of course this is not a case of anomaly. In case of bonding with H2O2 or OF2 or O2F2, it shows anomaly, or in case of peroxide. But here we have a normal case, so the oxidation state will be -2. Now with this knowledge, we can move on further. We can just write NaH2PO4 along with the oxidation state written on the top of each of these elements. Now, the given species is a neutral molecule. Therefore, the summation of all the oxidation state will be equals to 0. So for sodium, it will be 1 into +1. For hydrogen, since the count is 2, so it will be 2 into +1. We have already assumed that phosphorus will have an oxidation number of X, so X into 1. Then for oxygen, it will be 4 into -2. This will be summed to 0. If you multiply 1 into +1, we will get 1, 2 into +1, 2, X into 1, X, and 4 into -2, that means -8. Bringing on the variables on one side and constants on the other side, we get your X value as +5. Therefore, the oxidation number of phosphorus is +5. Moving on to the next species. So what is the next one? It is NaHSO4, in which we have to find the oxidation number of sulfur as it is underlined. Let us assume that the oxidation number of sulfur is X, and from the previous knowledge, the oxidation number of sodium will be taken as +1, hydrogen will be +1, and oxygen will be -2. Now, what was the compound? It was NaHSO4. Now this NaHSO4 is neutral in nature. Therefore, the summation of all the oxidation states will be giving 0. Now if you write it for sodium, since one sodium is present, so 1 into +1. For hydrogen, 1 into +1. Again for sulfur, it is 1 into X, and for oxygen, it is -2 into 4. If you just multiply 1 into +1, then it will give you 1, and 1 into +1, again 1, so 1 + 1, 2. Then 1 into X, it will give you X, and 4 into -2 will give you -8. We will bring on the variable and the constants on different sides. So X will be equals to +6 if you do that. Therefore, the oxidation state of your sulfur is +6. Moving on to the next question. We have H4P2O7. So in the H4P2O7, the phosphorus is underlined. If you assume that the oxidation number of phosphorus is X, then for hydrogen we know it, that the oxidation number will be +1. And for the oxidation number of oxygen, it will be -2. Now again, let us put it in the overall situation. So what was the compound? It was H4P2O7. And if H4P2O7 is taken, then it is a neutral molecule. That means the sum of all the oxidation states will be equals to 0. So for hydrogen, it will be 4 into +1. For phosphorus, it will be 2 into X, and for oxygen, it will be 7 into -2 is equals to 0. multiplying 4 into plus 1 will give you 4, 2 into x will give you 2x, and 7 into minus 2 will give you minus 14. We will bring the constant on one side, so 2x is equals to plus 10. Then cross multiplying the 2 on the right hand side will give you x is equals to plus 5. Means the phosphorus is present in the oxidation state of plus 5. So this is your final answer. So we have calculated the oxidation states for all three given underlined atoms. Moving on to the next question. What are the oxidation number of the underlined statement in each of the following, and how do you rationalize your result? So I am taking H2S4O6 only. So there were more examples, but this one is an anomaly and a special one. We will see why it is an anomaly. What is our way to decide the oxidation number? So here we have sulfur underlined. So we will assume that the oxidation number of sulfur is X. Now, what will be the oxidation number of hydrogen? It will be plus 1. And for oxygen, it will be minus 2. Further, if we just write the oxidation number on the top of each and every element, so H is plus 1, S is X, and O is minus 2. Now for a neutral molecule like H2S4O6, we know that the sum of all the oxidation number will be equals to 0. That means 2 into plus 1 plus 4 into X plus 6 into minus 2 is equals to 0. Or upon simplifying, 2 into plus 1, 2, 4 into X, 4X, and 6 into minus 2, minus 12. Then bringing the variables and constants on their sides. So 4X is equals to 10 or X is equals to 10 by 4. Here, the number which you are getting is not an integer, a positive integer. In place of that, what we have is a fraction. The need of the hour is to justify this oxidation number. Why? Because oxidation number cannot be fractional. We already know that oxidation number is something which is a hypothetical situation demanding the oxidation number as your charge in the case your compound is ionic. But charge can never be negative. We know it from quantization of a charge that it can only be a multiple of E. So there must be something missing here. So the problem is that here we have different kinds of sulfur in the same given compound. Means the sulfur will show different oxidation state in this compound. Now here is a picture to know that. So this is the bond connectivity of your H2S4O6. You can see it very clearly that on the terminal sides, the sulfur is attached to some other heteroatom, whereas the middle two sulfurs are not attached to any other different heteroatom. Instead of that, it is attached to its identical species. As a result of that, the terminal sulfurs will have an oxidation state of plus 5. How it is coming? Because it is attached to 2 oxygens and 1 hydroxides. So the 2 oxygens will give minus 2 and the 1 hydroxide will give you minus 1. So total of minus 5 can be satisfied with a plus 5 oxidation state. So that can be said for both terminal sulfurs. But if you look upon the middle sulfurs, so they are attached to sulfur only. As a result of that, it can have a maximum oxidation state of 0 only. Therefore, the oxidation state that we are seeing is not the ultimate one, but the average oxidation states of 4 sulfur. I hope you got my point. You can just take an average of it. So 5 plus 5 plus 0 plus 0 divided by 4. So that means 10 by 4, which is your 2.5. Moving on to the next question, you have to justify that the following reactions are redox reactions. So here we have copper oxide reacting with hydrogen to give us copper and water. In the B, we have iron oxide reacting with carbon monoxide to give you iron plus carbon dioxide. So let's start with the first reaction, which is given in option number A, in question number A. So it is CuO in solid form reacting with H2 in gaseous form to give you Cu in solid form plus H2O in liquid form. Now the first step to identify a redox reaction is to assign the oxidation number. If you do it, For copper, it will turn out to be +2 because oxygen will show no anomaly here. That means its oxidation state will be -2, making copper's oxidation state to +2 so that the compound can be kept at neutral state. Whereas the H2 is present in the elemental form, so the hydrogen will have a 0 oxidation state, whereas the same can be said for copper. But in the case of hydrogen and oxygen in water molecule, oxygen will get a -2 oxidation state and hydrogen will get a +1 oxidation state. What is our next thing? It is to look upon the change. So if you look upon the copper, the oxidation state of copper is decreasing from +2 in the copper oxide to 0 in the copper. That means copper oxide must be undergoing reduction because the oxidation number is decreasing. That means it must be accepting electrons from different species. And whenever a substance accepts electron, it is a case of reduction. Then after, if you look upon the oxidation number of hydrogen, then it is increasing from 0 in the hydrogen molecule to +1 in the water molecule. That means the oxidation number is increased by removing electrons. So that is the only possible way to increase the oxidation state. So this is the case of oxidation of H2 to H2O. Now you can think about both of these half reactions in terms of classical concept. How? Here the copper is being formed by removing one oxygen from the copper oxide. So you are removing an electronegative element from CuO. That is a classical definition of reduction. Similarly, your hydrogen is added to oxygen. So your hydrogen is getting oxidized due to the addition of one electronegative element. So from both perspectives, we can say that your CuO is getting reduced and your H2 is getting oxidized. Now the question is being asked about the situation of this reaction, whether it is redox or not. Now from the above discussion, it is very clear that reduction and oxidation is occurring simultaneously in this given reaction. So the reaction is redox reaction. Moving on to the next question, question number B. So let us write the question number B. It is iron oxide reacting with 3 moles of carbon monoxide to give us 2 moles of iron and 3 moles of carbon dioxide. The first step is to assign the oxidation number for each element in the given species. Then for iron, we will get it as +3. For oxygen, we will get it as -2. It's very obvious. So the charge coming from oxygen is -6, 3 into -2. And to make it equals to 0 for the whole species, you have to keep +3 for iron. So that will give you +6 from iron itself. Similarly, for carbon monoxide, the oxygen is having a -2 oxygen state. So the carbon will have a +2 oxygen state. Now, what about this iron which is present in elemental form? So it will have a 0 oxidation state because it is not attached to any other element. Then coming on to the last species of the product, which is carbon dioxide, oxygen is having a -2 oxygen state. So 2 oxygens will make up -4 charge. Now to make this compound neutral, carbon will get a +4 charge or +4 oxidation state, not charge, +4 oxidation state. What can be inferred from the examination of this oxidation state? It can be easily said that the oxidation number for iron is decreasing from +3 in Fe2O3 to 0 in Fe. That means your iron is getting reduced from Fe2O3 to Fe. Again, this can be explained on the classical basis because electronegative element is being removed from iron. That is, your oxygen is removed from the iron to make it into simpler iron molecule, iron atom. Then we have discussion about carbon monoxide. Here the carbon is having a +2 oxygen state and it is moving on to +4 oxidation state in carbon monoxide, carbon dioxide. That means the carbon monoxide is getting oxidized due to the increase in oxidation number of carbon in CO to +4 in carbon dioxide. Again, this can be explained on the classical basis because carbon monoxide is being added with one oxygen. So it is an example of classical oxidation. What about the reaction? So the overall reaction can be named as a redox reaction because the oxidation and reduction are undergoing simultaneously in this same process. Moving on to the next question, you have to write formulas for the following compound. We have mercury 2 chloride and nickel 2 sulfate. How can we do it? Yeah, it's very simple. We'll start with the mercury 2 chloride. We can say that in mercury 2 chloride, the oxidation number of mercury is given as +2 because of the Roman numeral written after mercury, which is 2 in the bracket. Then we know it. Conventionally, chlorine gets a -1 oxidation state, and we will take that same conventional value. The next step is to use the information of neutrality. So to make the compound neutral, you have to balance the positive and negative charge or positive or negative oxidation state. If you do that, what will happen? We have to form an equation. First, we are assuming that the number of chlorine atom is X. Then we can write for neutrality +2 into 1 for mercury. So that will give you +2 itself, plus X into -1 for chlorine. That will be equals to 0. If you solve it for X, you will get 2 as the number of chlorine atoms. Moving on further, we can just clearly say that 2 chlorine atoms will combine with mercury to form mercury 2 chloride. So from this information, we can write the formula of compound as HgCl2. Moving on to the next one. What is that? It is your nickel 2 sulfate. So for nickel 2 sulfate, what can we say? That nickel will show a +2 oxidation state due to the Roman numeral 2 written against nickel in brackets. Then after, for sulfate, the charge is 2-, and it is very clear from our previous discussion that for charged species, the oxidation state is always equals to its charge. The sulfate will get a -2 oxidation state. Then after, to make the compound neutral, we will again balance the positive and negative charges. How we'll do it? Our first step is to take the oxidation state of nickel as X. So let us assume the number of, not oxidation state, the number of sulfate groups is as X. Then after, for neutrality, we can write +2 into 1 for nickel, X into -2 for sulfate is equals to 0, or X is equals to +1. Therefore, the sulfate groups present in the given compound to form the nickel 2 sulfate is 1. Hence, the formula of the compound is NiSO4. I hope this is clear to you. Moving on to the next question, MnO4 2- undergoes disproportionation reaction in acidic medium, but MnO4- does not. Give reasons. How can we do it? One thing is for sure, if you want to see disproportionation reaction, your element should have an intermediate oxidation state for its convenience to get oxidized and reduced both. Now, why intermediate? Suppose if it has a maximum or minimum oxidation state, then what will happen? It cannot oxidize or reduce. Okay, so if it has a maximum one, means it cannot be further oxidized. If it is a minimum one, then it cannot be further reduced. If you take the case of MnO4 2- in acidic medium and write the reaction for it, then it will be MnO4 2- plus 4H plus giving us 2MnO4- MnO2 and 2H2O. Now, you can write this equation. It will make your things simpler. But from the previous information also, you can say that the MnO4 2- can undergo disproportionation. How? Let's see. So what is the equation that we got? It is MnO4 2- plus 4H plus 2, giving us 2MnO4- MnO2 and H2O. Now, by looking just at the compound, you can assign the oxidation state. Now here, manganese will have a +6 oxidation state in MnO4 2-. Now this oxidation state is an intermediate one. So it can go from +6 to +7. And this is seen in the acidic medium. It is going to MnO4- where the oxidation state of manganese +7. Similarly, it can also get reduced. Now talking about the increase, due to this increase, it is undergoing oxidation. Due to its increase in oxidation number by +1, it can be lower than +6. It can have +4, +2. Plus, it can be greater than +6, which is +7. So this oxidation state is an intermediate one. So from this also you can say that MnO42- can undergo disproportionation reaction. Why it is going under your reduction? Because the oxidation number of manganese is decreasing from +6 to +4. Moving on further. So we can finally conclude that MnO42- undergoes disproportionation reaction in acidic medium. Now let's move on to the next species, which is MnO4-. What is the reaction that is shown by MnO4- in acidic medium? So MnO4- plus 8H plus 5 electron will give you Mn2 plus 4H2O. Here I have written the oxidation number. You can write it by yourself also. But what can be inferred from the oxidation state? So manganese has a +7 oxidation state. Now this oxidation state cannot increase further. It is the maximum oxidation state that can be shown by manganese. Hence, manganese cannot undergo oxidation because it is in the highest oxidation state. But it can show a decrease in its oxidation state by moving on to Mn2+. Therefore, it can undergo reduction. Finally, we can conclude that MnO4- cannot undergo disproportionation reaction because the oxidation state is not intermediate but the maximum one. It can be moved on to a lower one, but it cannot be moved on to a higher oxidation state. So it can only oxidize and not reduce. Finally, you can conclude by saying that MnO4- is acidic medium, do not undergo disproportionation reaction. Then next question, balance the following equation by oxidation number method in acidic medium. How do we do it? The first step is to write the skeletal ionic equation. So I2 plus 2NO3- giving us NO2 plus IO3-. Then after, we will assign the oxidation number for each atom involved in this reaction. After that, I2 plus NO3 is giving INO3- is giving us NO2 plus IO3-. Here, the I2 will show a zero oxidation state because it is present in the elemental form. Okay. What about the other species? So nitrogen will show a +5 oxidation state. How? Because 3 into -2 from oxygen, -6. The compound is overall charged, having a -1 charge. Now, to keep the charge to -1, you have to assign a +5 oxidation state. Similarly, on the IO3-, we have one negative charge. So 3 to just 6 -1, that is +5 for iodine. Then after, the NO2 is completely neutral. So -4 charge is coming on from oxygen due to 2 oxygens. And that can be neutralized by +4 oxidation state of 1 nitrogen. What is the next step? So we'll do this reaction, this by ion electron method. Okay, not by an electron method, but the other one. So here, you will then identify that which is getting oxidized and which is getting reduced. If you see in the given equation, then iodine is getting oxidized and nitrogen is getting reduced because iodine is showing an increase in oxidation number from 0 to +5, whereas the nitrogen is showing a decrease in oxidation number from +5 to +4. The next step is to see the amount of change. So how we will calculate it? It's very simple. So this was the equation. In this, the oxidation number of iodine is changing from 0 to +5. So there is a 5 change magnitude. Okay, change in magnitude by 5. But for 2 iodine atom, if you calculate it, what it will be? Okay, 1 iodine atom, it will be 5. Okay, so per iodine atom, it is 5. But for 2 iodine atom, it will be 10. Because on the left hand side, we have 2 iodine atoms. So we will conclude it for the maximum one. Whereas in the case of nitrogen, the oxidation state is changing from +5 to +4. Therefore, there is a decrease in oxidation number. And for per nitrogen atom, that decrease is 1. Now what you will do to make it equal, the decrease and increase in oxidation number, you will multiply by 10. The one which is lacking that change, you will multiply it by 10. So let's do it. So this is the equation that we got, and now we are trying to equalize the increase and decrease of oxidation number and the atom as well. For that, you will multiply the iodate by 2. So this is done for equalizing the number of iodine atom, because iodine atom is having 2 count on the left hand side and 1 count on the right hand side. Whereas for the nitrate and nitrogen oxide, we have to multiply by 10, because the increase in naught equals to 10, which is seen in the case of iodine. If we do both of these operations, so I2 plus 10 NO3 minus will give you 10 NO2 plus 2 IO3 minus. Moving on further, what is the next step? We already balanced the increase and decrease in oxidation number and the number of nitrogens. Now we need to equalize the ionic charges. For that, we will be adding 8H plus on the left hand side, because 2 negative charge is on the right hand side, where on the left hand side we have 10 negative charge. So we will add 8H plus to make, or you can say to neutralize 8H, to neutralize 8 negative charges, and that will give you 2 negative charges on both sides. So this is your equation. What is the next step? Now we need to balance the hydrogens. How will balance it? By adding 4 H2Os onto the right hand side of the equation. If you do it, you will get I2 plus 10 NO3 giving us plus 8H plus giving us 10 NO2 plus 2 IO3 minus plus 4 H2. So this is your final balanced redox reaction. Here, the reaction is balanced because the charges and atoms all are present in equal number on both sides. So this was all for today's lecture. I hope you enjoyed the session. Thank you for joining it.